And then let's go ahead and continue. Let's review what we did last time. We're continuing chapter 8, section 5, which was integration of rational functions using partial fractions, indeterminable or irreducible functions. We're looking at rational functions. Here are the conditions. The integrals of rational functions, where the numerator, the degree of the numerator has to be less than the degree of the denominator. What kind of fraction is that if the top is smaller than the bottom? No. What's the name of it? We have proper, improper, we have complex. What kind of fraction is it? It's a proper fraction. Proper fractions are those in which the top number is less than the bottom number, because a fraction should be between 0 and 1. So the degree of the numerator has to be less than the degree of the denominator. If it's not, then we have to use long division and only further deal with the remainder, which we'll look at an example in a second. The denominator must be factorable to a point that's irreducible. In other words, you should be able to factor the denominator until you can't go any further. When we have to get to a point where one of two things happen. Either your denominator is made up of linear factors, binomials, x plus whatever, they have to be linear, or it's irreducible quadratic equations. In other words, it's a quadratic function that can't be simplified any further, can't be factored. So you have to take as far as you can. If your denominators have linear factors, then our numerators, when we look at the partial fractions, the reason it's called partial fractions is because we start off with an original fraction, the f over g, and then we break it down to depending on how many denominators we have. For example, if one of our linear factors has a multiplicity of n, then we have to look at all the possibilities, all the factors from the multiplicity of 1 to 2 to 3, all the way up to that. We have to look at each one of those separately and then allocate a numerator for those. Those are the examples we did last time, because all of our denominators were factors of linear factors. Now, today we're going to look at, we have irreducible quadratic factors on the bottom. X squared plus p of x plus q. You can't go any further with that. If that happens, our numerator now changes. Because we have a quadratic denominator, our numerator has to be a linear equation, degree 1. But remember, the numerator has to be less degree than the bottom. It exists in this one. This degree of this one here is 1. So the top one, the degree is 0. Anything to the 0 power is 1, so you just have the numbers. You don't have any x's. If you have a quadratic on the bottom, you have to have a linear on top. These are the examples we're going to look at today. And if you remember the length it took to solve the last one we did last class, it all goes down now to solving matrices, 3 by 3 or n by n matrices. So far, so good? Yeah, this is just a summary of what we talked about last time. It's also in the packet I gave you before we took off. It's in there somewhere. I just summed it all up for you. Let's look at example 2. where we left off last time. Use partial fractions to integrate this rational function. So what we have here is we have our 6x plus 7 over x plus 2 squared. So how many partial fractions are we going to have here? Well, actually, I don't need that just yet. Not that. With that, we're going to have how many? 2. Yes. Why 2? Because the multiplicity of the denominator is 2. So what we're going to have here is we're going to have one partial fraction that's just x plus 2 to the power 1 plus the second one, x plus 2 to the power 2. Can we have multiple or different types of denominators? Or can we have the quadratic and linear? Yeah. There is no limit of what we can use, what we can have. So what we have to do now is we have to figure out what A and B are. How do we do that? We have a fraction. I need a dx there. We have fraction and we have an equal sign. What do we do to get rid of the fractions here? Multiply everybody by the LCD. So multiply each term by the LCD, which is x plus 2 squared. Because we're trying to get A and B by themselves. So in the first one, the x plus 2's cancel, gives us 6x plus 7. One of those x plus 2's cancel. And then both, we just have this. So now what do? Get rid of the parentheses. So we have ax plus 2a plus b. So what do we know so far? We have to match this side with this. So the x's, we have 6x is equal to ax. 7 is equal to the constants, 2a plus b. So divide by x both sides. We know that a is equal to 6. Since we know a equals 6, we can now solve for b. So 2 times 6 plus b, so it's 7 equals 12 plus b. B is equal to -5. A is 6, and that's x plus 2. B is -5, x plus 2 squared. Oops. Because what are we trying to do here? What is the ultimate goal? We're trying to integrate this polynomial here. So the integration of that side is equal to the integration of these partial fractions. In other words, we don't have to do this, the left side, because it's going to equal to this. It's much easier for us just to worry about this. So this one, 6 is a constant. We have 1 over x plus 2 dx. The -5 is a constant, so we have -5 integral of 1 over x plus 2 squared dx. So right now we can rewrite these. This one's pretty easy, but this one has an exponent, so we have to worry about that. Right out of space. What's the integral of 1 over x plus 2 dx? It's the ln of x plus 2. Now we got to figure out, let me write this down so I can put it back up. So it's 6 ln x plus 2. What do we do here on this part? How do we take the integral of this one? Hmm? Yes. Yes. Because remember, whenever you have an integral of u to the power n, it's going to be u to the power n plus 1 over n plus 1. So this one, since the denominator is just going to be 1, I mean, the interior going to be 1, this is going to give us x plus 2 to the power -1 over -1. Six ln x plus 2. The negative makes it a positive. 5 x plus 2 to the power -1. What are we missing? Plus c. Very good. Because these are all indefinite integrals, we need to have that constant answer. So our final answer is that. All right. Now, the next example we're going to look at. Let's see if you could distinguish what's different about this one. Now we have this one. It's what? What kind of fraction is it? Improper fraction. Why? Because the degree on the top is bigger than that of the bottom. We need to have a proper fraction. So we have to use long division to simplify it. So we have x squared minus 2x minus 3. That goes into 2x cubed minus 4x squared minus x minus 2. Does everybody remember how to do long division? Don't feel bad because I mean I have people after we talk about it, long division, they forget how to do it. You always look at the leading terms. What times x squared gives me 2x cubed? 2x. So now we take this number, multiply it to each of those. So 2x times x squared is 2x cubed. Positive times negative is negative. 2x times 2x is 4x squared. Positive times negative is negative. 2x times 3 is 6x. Then what do? Change the signs because we're going to subtract them. In this case, we change the signs. Now we add them. The leading term has to cancel. If it doesn't cancel, then you did something wrong. The second term cancels. So 6x minus 1x is 5x minus 2. We can't go any further. What's wrong here? It's supposed to be, it's supposed to be a 3. So this is our remainder. So our equation that we started off with can be rewritten as 2x plus 5x minus 3 over x squared minus 2x minus 3. So we don't have to worry about the left side anymore. We just have to worry about this part now. So that becomes the integral of 2x dx plus the integral of 5x minus 3, x squared minus 2x minus 3 dx. Is this a proper fraction? So we use partial fractions again. Rewrite what I had here. Fine. 2x dx. But the first thing I have to do is factor the denominator. So we factor out the number. What it says it has a second sign that's negative, that means the signs are opposite. Tells me the bigger number gets the negative sign. What times what is 3? When you subtract them, you get 2. 3 and 1. So 3 goes here and the 1 goes there. Let's just focus on this partial fraction side. Because we have 5x minus 3, x plus 1, x minus 3. Since we have two independent factors, linear factors, we have to find what a and b are. So what's my first step? Multiply everybody by the LCD. Multiply all three of these terms by the LCD, which is x plus 1, x minus 3, x plus 1, x minus 3, x plus 1, x minus 3. So those cancel. So we have 5x minus 3. The x plus 1's cancel. So we have a x minus 3 plus b x plus 1. Distribute, sorry, yeah, 5x minus 3 equals ax minus 3a plus bx plus b. So 5x has to equal to ax plus bx. And negative 3 is equal to negative 3a plus b. So how are we going to do that? No, add 3a to both sides. This is already a negative 3a. So we know that b is equal to negative 3 plus 3a. Plug that inside here. Do we need the x's? All of them have x's. Do we need the x's anymore? Not really. I mean, we're solving for a and b, not x. Because if I divided everybody by x, they're gone. So this is the same thing as 5a plus b. And in place of b, I put negative 3 plus 3a. Since that's a plus, I could just drop the parentheses. A minus 3 plus 3a. A plus 3A is 4A. Add 3. So A is equal to 2. Since A is equal to 2, I plug it in, solve for B. And B is equal to positive 3. So what that means, we can expand our equation to be 2 over x plus 1 plus 3 over x minus 3. Remember, all of this stuff is, let's simplify this one. So what we have here is the integral of 2x dx plus the integral of 2 over x plus 1 dx plus the integral of 3x minus 3 dx. What does this one become? The first one. Yeah, so it's 2, add 1 to the top and divide by 2. This 2 comes out in front. This 3 goes out in front. Cancel, so it's x squared plus 2 ln x plus 1, 3 ln x minus 3 plus c. And there's our integral. Look for the next example here. What do y'all think? It's just, it's pretty much straightforward what you have to do. Example 4 now takes us on a little bit of different path. Because now our denominator has been factored out into 2 separate parts. One's an irreducible quadratic equation, and one of them is a exponentiated linear term, linear factor. So what does that mean? Let's just look at what we have here. We have negative 2x plus 4 over x squared plus 1, x minus 1 squared. How many denominators do we have? 3. So we're going to have 3 parts. So for the first one, it's an irreducible quadratic equation because it can't be factored out any further. So that means our numerator has to be a linear equation. And the second one, we have x minus 1, which is that one. And then we have x minus 1 squared, which is that one, D. Because we just did one like this. If you have an exponent, you have to do it from 1 and 2 and 3. This is a quadratic, so it has a linear factor on top. Any questions? Because you have to be able to set this up first. You're looking at it, it's got 7 heads. Because this first one, because the denominator is an irreducible quadratic equation, its numerator has to be a linear equation, ax plus b. Since the other one, the second one, is a linear factor with a multiplicity, we have to go to the linear factor with 1, then 2. Right. We have not done this first one before. So now we multiply each term by the LCD, which is this, which becomes negative 2x plus 4. What goes in the second one? Since on the second one, we only have the x squared plus 1. Those cancel, so we have x minus 1 squared. The x minus 1, one of the x minus 1s cancel, so we have the x squared plus 1 times x minus 1. And then the other one is x squared plus 1. Is anybody having trouble seeing this? I'll go ahead and do it the long way also. The LCD is x squared plus 1, x minus 1 squared. 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 X minus 1 squareds cancel, leaving with x plus 1 on the D part. One of the x minus 1s cancel, which is c times that times that. X plus 1 cancels, which is ax plus b that, and these all cancel. If you don't see it algebraically, then put it in there and cancel things out. Before we continue, we have to fix this one. Because this one is ax plus b times x minus 1, x minus 1. Plus 1. So we got to FOIL these out first. So we have ax plus b times x squared minus 2x plus 1. FOIL these out. Hopefully by now you got that. And then we have to FOIL these together. It was x cubed minus x squared plus x minus 1. We got to do it again. because the ax plus b has to be multiplied to the x squared minus 2x plus 1. So ax times x squared is ax cubed. Ax times negative 2 is negative 2ax squared. Ax times 1 is ax. B plus bx squared minus 2bx plus b. That's all from this. Distribute the c and the d. We get positive cx cubed minus cx squared, cx minus c plus dx squared plus d. Equals negative 2x plus 4. Are those difficult? No, just a lot of writing. The more writing in a small space, the more chance of mistakes you'll have. So our next step is, can we combine any like terms? No. So our next step is now we have to group them. Since we have x cubes, let's look at all the x cubes here, all the x squares here, all the x's, and all the constants. On the left-hand side, do we have any x cubes? On the left-hand side? No. So that's 0 on the left-hand side. And now on the right-hand side, we only have an x cubed here and here. So that's a plus c. These are all the x cubes. Are there any x squares on the left side? Since there aren't any x squares, its coefficient is 0. On the right-hand side, let's find all the x squares. We have negative 2a, b, negative c, and d. So the x squared, the coefficients are negative 2a plus b minus c plus d. So that, we just look for all the coefficients of x squares. So we got rid of those as well. How about the x's? On the left-hand side, we have a negative 2. What x's do we have here? We have ax, negative 2b, plus c. So negative 2a, a minus 2b plus c. A minus 2b plus c. And the constant is 4. So my constant is 4. And that's made up, let me see, get rid of my x's here. That's going to be made up of b minus c plus d. So it's b minus c plus d. So what do we know so far? The only thing we know so far is that A is equal to negative C. So anywhere we see, or we can say that C is equal to negative A. You pick which one you want to substitute. You want to substitute A as negative C or C as negative A? Okay, so we use A as negative C. So anywhere we see an A, we put a negative C in there. Negative 2 times negative C plus B minus C plus D. Negative C minus 2B plus C. So we know that A is equal to negative C, which tells us that we have 0 equals negative 2C plus B minus C plus D. Negative C minus 2B plus C. Going from here to there to there. The C and negative C cancel. Negative 2C minus C is negative 3C. Now we can solve for B. So this tells us that B is equal to 1. So anywhere we see a B, we know that B is equal to 1. We got A is equal to negative C. 0 equals negative 3C plus 1 plus D. B is equal to 1. 1 minus C plus D. I just simplified what I could there. So A is equal to negative C. Negative 1 equals negative 3C plus D. Three equals negative C plus D. What do we do next? Since this equals D and that has a D and that has a D, we could put those two together. Since this is negative 1 plus 3C equals D, 3 plus C equals D. So we have, here we have this equation equals that equation. D equals D. Negative 1 plus 3C equals 3 plus C. Solve for C. Subtract C from both sides. Add 1. 3 minus 1 is 2C. So C is equal to 2. Since C equals 2, 3 plus 2, that tells us that D is equal to 5. And if C is 2, then A is equal to -2. We've just labeled A, B, C, and D. And where does all that stuff go? All that goes here, A, B, C, and D. So -2x plus 4, x squared plus 1, x minus 1 squared dx is equal to ax plus b over x squared plus 1 dx plus the integral of c over x minus 1 dx plus the integral of d x minus 1 squared dx. Where a equals -2, b equals 1, c equals 2, and d equals 5. See how my numbers are correct before I'm going further of my equation. All right, so what do we do with this first one? We'll call it B is 1. What's that? Well, because it's a monomial on the bottom, what we could do here, we can split them up into -2x over that plus 1 over that. So that broken into those two. So -2x goes out in front. Well, I should hold it. The derivative of the bottom is 2x So that negative goes out in front. So it's du over u, which makes it ln x squared plus 1. How about this next one? What is integral of 1 over x squared plus 1? That can't be ln because it's not du over u, because this would be 2x. There's no x on top. So here in this one, we have to use our integral chart. Go back in those charts I gave you at the beginning of the semester and look for what integral is this 1 over x squared plus 1. Let me save you some, yeah. So actually find them because you should have access to them at any time from here on out. Look for the integral of 1 over x squared plus 1. Where's your chart? You have to have them here because we're going to be doing all these different problems here. It's the inverse tangent of x. Look at the integral table that I gave y'all. It's one of those. This 2 goes out in front, so it's ln x minus 1. Check that d again, because that shouldn't be so big. B. Here, something's wrong here. I did d wrong. Because it has to equal 4. So 4, b is 1, c is 2, it has to be 5. I'm thinking one of those signs are wrong.
About that, but why, whenever you multiply negative two times negative three, isn't it positive two? Or is it different?
Which one?
0.
Here?
Yeah.
This side. So in place of a, yes, it should be positives. Well, let's see. It should be positive 2c. Should be positive c. Yes. Good. Now you tell me.
Wait, I was trying to make sure, I was like, why, there's something wrong.
So that instead of negative 3c, it should be positive 1c. So CBD. To B. So B is correct. That we know for sure. So we know that this part here would be C plus 1 plus D. On what's question? Okay, so here we have A equals negative C, so 0 equals 2 minus 1 is 1, CBD, and B equals 1. So 0 equals C plus 1 plus D. So it's negative 1 minus C is equal to D. And D is equal to negative B minus C. So here's what we gotta redo this part. So D is equal to D, which means negative C negative B is equal to three plus C. So we're back over here. We have x cubed, x squared, x, and a constant. Throw all that stuff away there. So we have 0 equals A plus C. 0 equals negative 2A plus B minus C plus D. Negative 2A minus 2B. And 4 equals B minus C plus D. So A equals negative C. Negative 2 times negative C plus B minus C plus D makes it 2C plus B minus C plus D. 2 minus 1 is C. Negative 2 equals negative C minus 2B plus C. The C's cancel. So negative 2 is negative 2B. So B is equal to 1. Minus C plus D, which makes it 3 equals minus C plus D. So that's that one, that's that one, that's that one, and that's that one. solve for D. So D is equal to negative C minus B. E is equal to negative C minus 1. So with these two, so we have D equals D, which is negative C minus 1, 3 plus C. So add C to both sides, subtract 3. So negative 4 equals 2C. So C is equal to negative 2. Since A equals negative C, then A equals 2. Then D, since negative 2 is 2 minus 1 is 1. There. Those are the problems. So B is 1, A is negative 2, C is, yes. So I can't use anything on this side. Okay, so now what we now have A is 2, B is 1, C is negative 2, D is 1. So we have the integral of negative 2x plus 4 over x squared plus 1 x minus 1 squared ax plus b plus b x minus 1 squared dx, where a is equal to negative 2, b is equal to 1, c is equal to 2, and d is equal to, I'll just do it again. 2, 1, negative 2, 1. 2, 1, negative 2, 1. Two x plus 1 over x squared plus 1 dx. Negative 2 over x minus 1 dx. 1 over x minus 1 squared dx. All I did was put in A, B, and C. I haven't changed anything else, so nothing else could be wrong there. This first one, I could split to 2x over x squared plus 1 plus 1 over x squared plus 1 minus 2 1 x minus 1 dx plus 1 over x minus 1 squared. So this is du over u, which makes it ln x squared plus 1. 1 over x squared plus 1 is still the inverse tangent of x. Ln x minus 1. Those are and this integral is x minus 1 to the power negative 2, which we did something that similarly earlier. Do we need absolute values in the first one? Why not? Can it ever be negative? No, because x squared is always positive plus 1, so ours is parentheses there. Plus the inverse tangent to ln. The other one has to because x minus 1 can be negative. Now, this one, the integral of this one. We have to add 1. So it's going to be negative 1 x minus 1 to the power negative 1 over negative 1 plus c. Ln x minus 1 minus 1 over x minus 1 plus c. There is your answer. That's the integral of that function we started off with. Be very, yeah, I can't stress enough, be very careful because one small sign error in the second step ruined the whole thing. I kind of knew something was weird because A was being ended up negative. And usually the leading term is never negative. Usually never, yeah. And also, if you notice the numbers, we had 1s and 2s. Having a 5 in front of this one is very difficult because we couldn't bring that up there and just have a regular function. So it's just the numbers didn't look right. Okay, that's example 4. Let's do example 5. Example 5, use partial fractions to evaluate this function. Use partial fractions here. So we have 1 over x squared plus 1 squared. We have two denominators, but this is a square, so we'll have 3 different terms. This one's going to be a over x, the first one, the first factor. It's a linear factor. Plus x squared plus 1. So this has to be bx plus c. And then we have the second part of the denominator, dx plus e. Everybody see why I have bx plus c, dx plus e? because the denominators are quadratic. Okay, now we have to do everything we did in the past. Multiply by the LCD. So you get 1 is equal to a x squared plus 1 squared, bx plus c times x squared plus 1 plus dx plus e times x. Again, if you don't see what happened there, then just put parentheses around each term and multiply by the LCD. Whatever cancels goes on the top. So we have to get rid of the parentheses. So we have to do this one first, which is x squared plus 1 times x squared plus 1. Multiply these two together, we get x to the 4th plus 2x squared plus 1. Multiply these two together, we get x cubed plus x. Multiply these two together, gives us b x to the 4th, bx squared, cx cubed plus cx. Multiply these two together, dx squared plus ex. Multiply these two, it's ax to the 4th plus 2ax squared plus a bx to the 4th bx squared cx cubed plus cx dx squared plus ex. Again, that's why I don't want you to just to bobblehead and copy me. I want you guys to work it out, because then if I made a mistake, you can tell me. All you're doing now is just copying me. If I made a mistake, then we won't find out till the very end. Don't do that. All right, so the only way we can check to see if you have the same thing I do, if you finish this, is now we have to start solving for here are all the x to the 4ths, x cubeds, x squareds, x's, and the constants. So how many, on the left side, how many x to the 4ths do we have? 0. There's no x to the 4ths. Now, matching, we have a plus b. Those are the only x to the 4ths that we have. How about x to the 3rds? We have none on the left side. We just have c x to the 3rd on that side. X squares, we have 0 there on the left side. So we have 2a plus B plus D. X's, we still have 0, which means we have C and E. And then for the constant, 1 is equal to A. So we have two of them. We have C is equal to 0, A equals to 1. So if C equals to 0, so we have C equals 0, that's done. If A equals 1, what's B? Yeah, so B is equal to -1. If C is equal to 0, then E has to also equal 0. And we know that A is equal to 1. So D is equal to 2 times 1 plus -1 plus D. 2 minus 1 plus D. So 0 equals 1 plus D. D is equal to -1. And that's the only way I could compare if my numbers are the same as yours. A equals 1, B is -1, C is 0, D is -1, E 0. Those look like normal numbers now. What do we do with those? Plug them in up here. And then take the integral of it. So we have the integral of 1 over x, this equation, is equal to integral of 1 over x dx. B was -1 x plus 0 over x squared plus 1. And then we have D was -1 x and E was 0.
Oh,
All over x squared plus 1 squared. So plug in everything we see there. What's the integral of 1 over x? Ln absolute value of x plus -x over x squared plus 1. -x over x squared plus 1 squared. How about the integral in the second one? -x over x squared plus 1. Remember, we can use substitution if it just involves numbers. In other words, is this du over u? So this negative can go out in front. But what's missing? If we take the derivative of the bottom, what's missing? So we can put a 2 there. If we put a 2 there, we have to get rid of it. So we have 1/2 ln x squared plus 1. Now we have another problem. What do we do with that one? Here, the negative goes out in front, so it becomes a negative x over x squared plus 1 squared. We don't have any formulas that deal with x squared plus 1 squared. We can use substitution. Let u equals x squared plus 1. So du would be 2x. So it's ln absolute value of x minus ln x squared plus 1 over 2. Do we have a 2 in front of the x? So we put it there. That means we have put a 1/2. So now it's du over u. So right now we have du over u, which means we can change it to u to the -1. So the integral of x squared plus 1 to the power -2 becomes x squared plus 1 -1 over -1. Which becomes -1 over x squared plus 1. So this integral becomes that. So that negative and that negative cancel. We have over x squared plus 1 plus c. Oop, and the 1/2 in front. There's that 1/2 right there. Any questions? These numbers look okay. They're all small. What more do we have? 3 more. We can do it. Examples. Well, they're not hard, it's just long. Example 6. This one's just asking find a, b, and c in partial fraction exponent. So find x squared plus 1, x minus 1, x minus 2, x minus 3. So that expands to a, x minus 1, b. Since these are all linear factors on the denominator, so we're just asked to find a, b, and c. Okay, let me see what. I'm trying to look for a trick to this one because it looks pretty straightforwardly easy. So if we multiply by the LCD, we get x squared plus 1 equals a x minus 2, x minus 3, b x minus 1, x minus 3, c x minus 1, x minus 2. So that becomes x squared plus 1, x squared minus 5x plus 6, x squared minus 4x plus 3, x squared minus 3x plus 2. There is a shortcut you can look for on these things. When you do those multiplications, I'm gonna show you a shortcut on how to do these. But first we have to do it the long way. So for the x squareds, the x's and the constants, we have a plus b plus c, negative 5a, negative 4b, negative 3c. 6a plus 3b plus 2c. So this one, the x squares equals 1. There are no constants there on the left side. So the coefficient is 1. So all the x squares have to equal 1. All the constants have to equal 1. Zero. Let's see. Now this looks familiar in the last question we did yesterday, because we have a matrix of 1, 1, 1, negative 5, negative 4, negative 3, 6, 3, 2, 1, 0, 1. We could do the same thing we did last time, but here's a shortcut. Because we have individual linear factors on the denominator, and it's a proper fraction, we can multiply by x minus 1, x minus 2, x minus 3 separately. And then enter the x values. Let me show you what I mean. So the first one, we're going to solve for A. So multiply to solve for A. Multiply each term by its denominator, x minus 1. So we have x squared plus 1 times x minus 1. A x minus 1 over x minus 1. Okay. Follow that so far? Now, what is the 0 of x minus 1? X minus 1 equals 0. So if we enter x equals 1 to all the x's in there, so we have x squared, what was that? X squared plus 1. So we did x minus 1. Okay, before we multiply, this and this cancels. That and that cancel. So we have x squared plus 1, x minus 2, x minus 3 equals A, B, x minus 1. So when we enter x equals 1, what happens? What happens to B and C? They both go to 0 because the top 1 minus 1 is 0. So all we have now is 1 plus 1, 1 squared plus 1, 1 minus 2, 1 minus 3, and that equals A. 1 squared is 1, 1 plus 1 is 2, 1 minus 2 is negative 1, 1 minus 3 is negative 2. So A is equal to 1. Do the same thing with B and C. To find B, multiply each term by x minus 2. Reduce, then plug in x equals 2. X minus 2's cancel on the original equation and the B. If we plug in x equals 2, we got 2 squared plus 1, 2 minus 1, 2 minus 3. That's gone to 0. That's gone to 0. That equals B. So B is equal to 5 over 1. So B is equal to -5. So I get -5 for B. Did you get -5 for B? What'd you get for C? Hurry up. Slackers. That's a shortcut I showed you. So to find C, what do? Multiply each term by what? X minus 3. Then cancel whatever you can, and then enter x equals 3. So those cancel. Those cancel. Enter x equals 3. So we get 3 squared plus 1, 3 minus 1, 3 minus 2. That goes to 0. That goes to 0. So equals C. 9 plus 1 over 2 times 1. 10 over 2. So C is equal to +5. Shortcut. Only works if all of the factors are linear factors on the denominator. Yeah, I bet we should go back and check each one that we've done originally. Okay, what about if we have quadratic denominators or linear factors, I should say, with multiplicities? Example 7. Find A, B, and C of this equation. X minus 1, x plus 1 cubed. So how many terms are we going to have here on our expansion? If it's an x plus 1 cubed, we'll have 3 of them. We'll have x plus 1, x plus 1 squared, and then x plus 1 cubed. So it's A, B, C. Here's step one. Now, these are a little bit different because now the steps here, first, multiply by LCD, which is x plus 1 cubed to each term. If I do that, what do I get? What happens to the first term? It simply becomes x minus 1. On the second one, we have only one of the x plus 1s cancel, so it's x plus 1 squared. Two of the x plus 1s, so we have x plus 1. And the last one, all of them cancel. So far, so good? This is kind of what we did last time. So since they're all the same ones, what do you think we plug in? -1, because we take this and set it equal to 0. We got -1 minus 1, -1 plus 1 squared, -1 plus 1 plus c. So it's -2 equals that's 0, that's 0. Now, what's the difference between this one and the last one we just did? Can we continue the same way we just did it? No. Why not? Because the powers change. The last one, it was always a linear factor. Since these have a multiplicity and they change, we can't use the same thing we did last time. But we can start off with this, which we have here. So now we take both of these. So we have x minus 1 equals x plus 1 squared plus b x plus 1, and c is -2, so it's -2. Now, because we have a power in our denominators, we take a derivative. Take the derivative. Differentiate this. It gives us what? 1 equals 2a x plus 1 plus b. So here, take the derivative. So everybody see, so derivative of x is 1. The a is a constant, leave it alone. So 2 comes down and times the derivative of the inside, which is 1. The derivative of this is 1. Now you plug in x equals -1 again, solve for the constant. So we have 1 equals 2a -1 plus 1 plus b. That goes to 0, so b is equal to 1. Now, since we know what b is equal, we plug it into this one. So we have x minus one equals a x plus one squared plus one x plus one minus two. Yeah, that'll take us a long way. That'll take us long because we'll have a lot of, because the next step we have to differentiate again. If we did this, we have too many terms. Let's just differentiate this one we have. Differentiate that one. So differentiate this one. The derivative of one is the derivative of 2a x plus 1, 2a. Because we take derivative with respect to x, the derivative of x is 1. The derivative of b is 0. So 0 equals 2a, therefore a is equal to 0. The coefficients can be 0. I mean, not coefficients, but the a, b, and c factors can be 0. So notice, the first thing we did was multiply by the LCD. Well, not the LCD, but yeah, the LCD. So we get a simplified version. Then we take the solution of the LCD. We took the x plus 1, set it equals 0, we got 1. We got the 0. We plug it in there and get a constant term. Then take the derivative of that. Plug in the x equals -1. Then take the derivative of that. Plug in x equals -1. So that's where we're done. So our answer becomes, what's 0 over x plus 1 plus 1 over x plus 1 squared plus -2 x plus 1 cubed. Oops, there. That's what we just plug in a, b, and c. That's all it's asking us to do. Yes, c is going to be pretty much the same thing. The last one's going to be the same thing. So, yeah, I hate to say it, but you notice how the shortcuts are always saved to the end? Think if we used these rules in the earlier examples. Think of how much paper we took. It'd be much easier.
Why did you wait so long? I forgot.
Well, because what I do is, and I know these, but I didn't think about them because I just look at the examples as they come through. And the examples they gave us fit these shortcuts. Then yeah, so we use those. Like this, I show it to you, or later on, if you find something when you're working out, you can figure out a shortcut, you can do those. So it just gets passed down.